we introduced Multiview Compressive Coding, or MCC, for 3D reconstruction. MCC is a system that inputs an RGBD image and outputs the full 3D reconstruction of the scene. MCC differs from most prior works in mainly two ways. First, while most prior works are category specific, MCC is category agnostic. Once trained, MCC can be used to reconstruct objects of any category. Second, when most prior works require full 3D meshes for training, MCC can be trained directly on video frames, making it much easier to scale up and enjoy the benefit of large-scale training. Here we present the reconstruction results on a wide range of different examples, including complex objects and even imagined objects from DALL-E 2. We can see that MCC is able to reconstruct 3D geometry even in these challenging cases. Let's now take a closer look at how MCC works. The high-level design of MCC is quite simple. Given an input RGBD image, we first unproject each pixel into its 3D XYZ coordinates using the depth. We then encode both the RGB image and the XYZ coordinates using an RGB encoder and an XYZ encoder respectively. The outputs of these encoders are then fused together to form an encoded representation R. A decoder then inputs a set of input query points along with R and predicts its occupancy probability and the RGB color. Finally, the set of occupied colored points forms our final reconstruction. The architecture design of each component is very simple as well. Our RGB encoder is simply a standard VIT for encoding an input image. Our XYZ encoder is also a VIT, except that we additionally handle the cases where a pixel's XYZ coordinate is unknown, due to, for example, sensor uncertainty. Specifically, if a pixel has a known XYZ coordinate, we linearly project it to some latent space, and if a pixel has an unknown XYZ coordinate, we'll use a special embedding to represent the coordinate of that pixel. Then, we use an attention-based patch embedding layer to convert each patch into a token vector, analogous to what a patch embedding in the standard VIT does. The decoder is, again, a simple transformer-based design. It first concatenates the representation R and the queries in token dimension, and then models all tokens together using transformer layers. One key property of MCC is that it takes only points as supervision. It does not require having access to a complete ground truth shape to train a model. And that is why we can simply train this on video frames. Second, our model is category agnostic, so during training, we simply train on all data from all categories at once. At inference time, it can operate on any objects, even those of unknown categories. Third, our default architecture is based on standard transformers. We do not handcraft any 3D specific architectures or bake in any 3D specific priors into this design. We show how to train a 3D model based on this simple transformer-based design and demonstrate its strong performance. Fourth, note that the encoder cost is amortized among all points, and each additional query point only induces computation at the decoder. MCC uses a lightweight decoder, so the overall inference is very efficient. Furthermore, note that MCC does not assume a fixed resolution, so one can generate output at any desired resolution at inference time. Finally, since MCC makes no assumption on the data, it naturally works not only on objects, but also on scenes as well. Given an input image of a scene, it completes the missing parts, such as the furniture, floors, walls, and so on, reasonably. Overall, our design philosophy is centered around simplicity and scalability. MCC's simplicity makes it easy to scale, and the scalability makes even a simple and flexible design very powerful. Let's next look at some experiment results. For object reconstruction, we train MCC on the Co3D dataset, which contains 37 short videos from 51 categories. We emphasize that we do not train category-specific models with MCC, but instead, we train only one model on all data from all categories. Here we present some results on holdout Co3D categories. The first column shows the input images. The second column shows the scene part of the object in 3D. The third column shows our reconstruction. We can see that even though MCC never saw these categories during training, it reconstructs these objects very well. To further test its generalization, we use our iPhones to capture a wide range of different objects in the wild, including a Quest 2, a Dyson, and even a spiral, which definitely is not part of the Co3D dataset. We see that MCC reconstructs all of them pretty well. We also test MCC on highly diverse internet photos from ImageNet. MCC generalizes well in these settings as well. Furthermore, MCC even generalizes well to imagined objects from DALL-E 2. These objects were certainly not seen during training. Finally, thanks to MCC's general design, it naturally works on scenes as well. Here are some qualitative results on hyperscene and taxonomy in images. Quantitatively, one important observation we would like to emphasize is that MCC shows very promising scaling behaviors. The performance steadily improves as it sees more data. Thus, we believe that further scaling up MCC to even larger data would be a promising future direction. In short, we introduced MCC for 3D reconstruction. It's simple and it generalizes well to a wide range of different settings. The code and models are available online. Please also check out our project page for more examples and details. Thank you.